SwayamPrabha. Digital India. Educated India.
A logical and systematic approach to solving organic chemistry problems for CSIR-NET. In the module 14, we will be looking at organic transformations and reagents. We will be mainly focusing on functional group interconversions, mainly oxidations and reductions. I am Professor Balaji, currently working at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, Ministry of Education, New Delhi. In this session, what we are going to learn, some of the things are given here. We will be mainly looking at various redox reactions or reagents. So some of the reducing agents we will be encountering are lithium aluminium hydride, sodium borohydride, dibol H, diisobutyl aluminium hydride, lithium and liquid ammonia, that's mainly used for bridge reduction, boranes and other catalysts. And similarly, we will also looking at some of the oxidizing agents. Some of them include manganese dioxide, rose bengal, selenium dioxide, and other things. So in the reactions or named reactions, what we will be looking at is Schlunk-Ien reaction, Henbest modification of Ullkushner reduction, Corey-Suggs reagent, Baeyer-Villiger oxidation, Mainwall rearrangement, Sharpless epoxidation are some of the reactions which we will be encountering. So let us start with the first problem. So in this worked out problem, this question was asked in June 2014. The correct combination of reagents for effecting the following sequence of reactions. So a substrate 1,4-cyclohexadiene is given. It is converted into a endoperoxide and with one of the double bond is intact, and in the final product that double bond is not there. So that means basically a reduction reaction had occurred. So 4 different reagent combinations are given. One is ozone and oxygen, that is a reagent A, and for reagent B, potassium azodicarboxylate in the presence of acetic acid is given. And in the second combination, oxygen with rose bengal and HNO, that is photochemical condition, that is the condition A. And in the second condition, it is again potassium azodicarboxylate in the presence of acetic acid. And the third reagent, that is combination given, is oxygen with rose bengal in the presence of photochemical conditions, and B is the hydrogenation reaction in presence of palladized carbon. And the fourth one is the same reaction, that is oxygen and rose bengal, but this time it is heating conditions, and the second reactions is basically with hydrogenation in the presence of palladium carbon. So there are 4 different combinations are given for A, condition A, and condition B. We are going to find out what is the right condition for this particular transformation. So let us look at the reagents, because since we have multiple reagents, we have to identify which reagent will carry out what type of reaction. Based on that, we have to decide what combination is going to work here. So let us look at the reagents, what they will mainly do. O3, that is nothing but ozone, is mainly used for ozonalysis, that is formation of ozonide. That is the main thing. And the second reagent is actually either a reducing conditions or oxidizing conditions, cleaves that ozonide to give the dicarbonyl compound. So here we are only given ozone, that means we will be ending up only with the ozonide. And the another reagent is potassium azodicarboxylate. This, when treated with acetic acid, that is in the presence of acidic reagent, it gives diimide, because this diimide is basically a quite unstable reagent, and the effect of this diimide is basically it will reduce a double bond. So this is the second reagent, and the reaction is given here. The potassium azodicarboxylate when treated with acetic acid gives the diimide as the in situ it is generated. Then the next one is the rose bengal. So the structure of rose bengal is actually given here. This is mainly used as a triplet sensitizer, and it gets activated in the presence of light, that is photochemically it is activated, and this converts basically the oxygen, triplet oxygen is getting converted to singlet oxygens. So that is the role of this rose bengal under photochemical condition. It transforms the triplet oxygen into a singlet oxygen. And the last one, and this reaction generally is called as a Schlunk-Ien reaction. And the last one is the hydrogen and palletized carbon condition. So this
Palletized carbon does not break oxygen-oxygen bond.
So if you look at what are the possible things, the ozone is not possible because here we have basically a peroxide is formed. So when the peroxide is formed, ozone cannot give the peroxide. So this is ruled out. And in the last one, if you look at hydrogen palletized carbon, basically breaks the OO bond. So that means, but in the final product, we have the OO bond. So that means this reagent is also ruled out. So the only two combinations left out are potassium azo dicarboxylate and O2 and rose bengal combination. So let us look at how the reaction actually proceeds. So in the presence of rose bengal and oxygen, photochemically is getting converted, the triplet oxygen is getting converted to singlet oxygen. So this is the first step that happens. So once this singlet oxygen is formed, this is a highly reactive species. So we have a 1,3-diene that is present here. So when we have a 1,3-diene, that will undergo 4+2 cycloaddition reaction, or basically the Diels-Alder reaction will be carried out under this photochemical conditions. So we will end up with a bridged endoperoxide. So that is what is the product that will be formed. So this alkene, and we have the oxygen OO double bond. So these two will form like this. So we end up with a Diels-Alder reaction, and the Diels-Alder reaction produces the bridged endoperoxide as shown here. So this is the first step. And in the second step, what happens is the potassium azo dicarboxylate in the presence of acetic acid produces the diimide. So this is the reaction that is happening, and this diimide is quite unstable reagent. So that is generally this is generated in situ in this reaction. And the speciality of this particular reagent is it is generally used in the transfer hydrogenation reactions. So basically, when we are doing a reduction reaction, in most of the cases, hydrogen gas with a noble metal is generally used for the reduction reaction. Hydrogen in the presence of palletized carbon, or hydrogen in the presence of platinum, or hydrogen in the presence of other rhodium and iridium catalysts are generally used for the hydrogenation reaction. So these are called the direct hydrogenation reactions. But in this particular case, where we are using diimide, we do not have a hydrogen gas as the source for hydrogen, but the diimide itself transfers the hydrogen. It has two hydrogen atoms. So these two are transferred across the double bond. In other words, we can carry out the reduction without actually using hydrogen gas. So that is what is called transfer hydrogenation. And this diimide specifically transfers the two hydrogen atoms across the double bond in a very, very specific way. So what type of double bonds will be reduced by this diimide? So the diimide has a very specific character. It will reduce only the symmetric double bond. That means CC double bond, CC triple bond, NN double bond, or even sometimes OO double bond. So these are all the double bonds where the symmetrical atoms are there. They only reduced by this diimide. But when we have a carbonyl group, or a C double bond N, or N double bond O, or O double bond S, these type of double bonds are not reduced by the diimide reagent. So in our case, we have a carbon-carbon double bond that is present here. So when we have a carbon-carbon double bond, that is basically a symmetric double bond. So this will be this can undergo reduction in the process of diimide. So this reaction actually is a very specific reaction. In other words, we say this is this follows a concerted mechanism, and this leads to the cis addition. Like when the metal catalysts are used for hydrogenation, there also we will get the cis addition. Similarly, diimide reaction also gives a cis product. So in this case, it is a symmetry allowed product, and that hydrogens are transferred in a same side, that is a cis fashion they are transferred. and we end up with the reduced product. So this is the overall reaction that is happening here. So the reagent for the conversion of the cyclohexa 1,3-diene to the endoperoxide is through the use of rose bengal and oxygen in the presence of light, and the second reagent is potassium azodicarboxylate in the presence of acetic acid. So let us move on to the next problem. This question was asked in June 2014. So here the reagent A that is used and the major product that is formed B in the following reaction sequence we have to identify. So there is a cyclic lactam is given here, and that is treated with some reagent A, undergoes reduction of the carbonyl group. So that is the first thing happening. And then when we use cyanogen bromide, what happens is the cyclic system opens up and we are supposed to get some product. Because if you look at all the three products, there are three combinations which are given in which the cyclic system is opened up. There is only one product where the cyclic system is not opened up. So these are all the four different combinations that are given as a probable product that could have been formed in this reaction, and we have to identify what is the actual product that is formed. So the first reagent given is lithium aluminum hydride, that is a reducing agent, and the opening up of the beta lactam ring, actually the reduced cyclic amine ring opens to give the substituted derivative. So that is the first combination. And in the second one also we have lithium aluminum hydride as a reducing agent. Third one has sodium borohydride, and the fourth one has hydrogen and palladized carbon. So if you look at very carefully, sodium borohydride is not a strong reducing agent to reduce a amide bond, or in this particular case lactam bond. So this can be ruled out. And similarly, hydrogen and palladized carbon is generally used for the reduction of double bonds. So that also we can rule out here. So the only thing left out is either it is the lithium aluminum hydride with whatever could be the product. The B is the one we have to identify what is going to be the product. So the reducing agent that we have to use is mainly lithium aluminum hydride. So let us look at how the reaction actually proceeds. In the first step, addition of the hydride ion from the lithium aluminum hydride takes place. This actually adds to the carbonyl group. That carbonyl group actually takes the reduction takes place on this one. So here we have a hydrogen atom that is transferred from this particular lithium aluminum hydride, and we end up with a aluminum alkoxide complex. The oxygen aluminum bond is formed after the transfer, because when the charge transfer takes place, when the hydride ion adds here, so the oxygen will get the negative charge, and this aluminum will now form a bond with this oxygen to give the aluminum alkoxide complex. Then what happens is oxygen is electronegative in nature, and there is a neighboring nitrogen atom having a lone pair of electrons. So the shift of lone pair of electrons from the nitrogen actually takes place. So that results in the formation of an iminium ion, and with concomitant loss of the alkoxide groups, that aluminum alkoxide is lost. So we end up with an iminium ion. So now this iminium ion has to undergo some further reduction. So we have a nucleophile, that is a hydride ion that is present in the lithium aluminum hydride. So this adds to this alkene carbon, and with the double bonded pi electrons are moving towards the nitrogen atom to neutralize its positive charge. So we finally end up with a cyclic amine as shown here. So here basically there are two hydride ions are added to the system. So the carbonyl group is completely lost in this particular reaction. So we end up with a reduction of the carbonyl group, leading to the amine, cyclic amine in this particular case is happening. So what we can say is the beta lactam's carbonyl group is reduced by lithium aluminum hydride to give the cyclic amine. And if we move forward, what happens is we have the basic nitrogen that is present here, and this is going to react with the cyanogen bromide. So that is the next step, because the reagent here now A is nothing but lithium aluminum hydride. So That is what is the first one. So we are now going to find out what is the product B that is formed in this reaction. So the product B is formed after the reaction between the cyclic amine and the cyanogen bromide. So if you look at the structure of the cyanogen bromide, this carbon is having little bit electrophilic in nature. Nitrogen has a lone pair of electrons. So this nucleophilic nitrogen attacks the central carbon atom with the concomitant loss of the bromide ion. So what we can say now is the nitrogen is having a positive charge with the cyanide group attached to this. So what happens, nitrogen with a positive charge is not quite stable. So some additional reaction also has to happen. So in the next step, what happens is the liberated bromide ion actually attacks the neighboring carbon atom. So when it attacks the neighboring carbon, the carbon nitrogen bond is broken towards the nitrogen atom to neutralize the charge on the positive nitrogen. So we end up with a ring opening of this particular amine after the addition of cyanide and the bromide ion happens. So here the final product that is formed is the 3-bromo-propyl methyl cyanamide. So that is the product that is formed after the attack of the bromine. So with that we can say the reagent is lithium aluminum hydride and the product formed is the 3-bromo-propyl methyl cyanamide. So this is the final product, that is B, that is formed in that reaction.